Yeah, so hello everyone. Today we're going to be looking at some functional equations. So we'll start off by looking at what a function is. So does anyone know what a function is? Feel free to unmute and ask questions and whatever in the middle of the session. So yeah, a function, what I'll say a function is, it's like a mystery box, kind of. So it takes in some value. I'll put in some value x into the function and it will output some other value y. And I'll call this function f. So yeah, all kinds of different values it can take in and it can output all kinds of other different values. So let's call the set that it can take inputs from. Let's call that set S for now. And of course, there is going to be a set which it can output to, and I'll call that set T. So I'll denote a function by f. It goes from S to T. I hope that's fine. So yeah, basically for every single value in S, suppose there's an x in S, there's a y in S, okay, not y, but let's say there's an a in S, there's a b in S, there's a c in S. All of these values, there is some value in T that f will output some other x or like y, z, w for each one of these values. But a function won't be like, okay, you input a one time into the mystery box and it will give you y. And then if you input it another time, it will still give you y. It won't give you z or something like that. So yeah, that's what a function is. So to be more concrete, let's give an example for a function. So a function going from the set of integers to the set of integers, it can be something like f. It can be something like, okay, so for every single x, it will give us x plus 1. It will output x plus 1. So this is a function because its output is determined, right? We know where it's going to go. And the same value of x can't go to two different values of f of x. So I'll call this value, the value the function outputs, I'll call it f of x. So in this case, f of x is equal to x plus 1. And I'll call this set is the domain, and this set is the codomain of f. This is all standard terminology. So yeah, and wait, okay, yeah, can you still see the screen? Okay. Yeah, so f of x is x plus 1. So what this function does is it sends 1 to 2, it sends 2 to 3, it sends minus 1 to 0.
क्या हुआ?
एक ही बोले बात ऐसे है चार पे।
Oh, अच्छा.
Yeah, so this function sends 1 to 2, minus 1 to 0, 2 to 3, and so on. So yeah, that's what functions are. And it's important to note that a function might not always cover the set z in cover the codomain, cover set z or cover the set t entirely. What I mean by that is, suppose we have a function which is like f goes from z to z, and this function looks like f of x is equal to x squared for all x in the integers. Okay, so yeah, by the way, z denotes integers, q denotes rationals, r denotes reals, and n is going to denote natural numbers, which is 1, 2, so on and so forth. So no 0 in the naturals. But yeah, so for f of x is equal to x squared, this function is only going to cover the square numbers, which is 1, 4, 9, 0 as well. 0, 1, 4, 9, 16, so on and so forth. So this set, which is going to be a subset of z, this is called the image of f. And this might not be equal to z. In this case, it's not. It might be equal to z. So in f of x is equal to x plus 1, it is equal to z, because for every integer x, the number x minus 1, the f of that is going to be x. So every single thing is covered. So yeah, that's the basics of what a function is. Some other properties of functions are, Well, we'll not look into that right now. Okay, so what is a functional equation? A functional equation is going to be, you're going to be given a function, and you're going to be given some domain and some codomain, and you're going to be asked to find all functions that satisfies some relation of sorts, like say f of x squared plus f of x y is equal to f of x times f of x plus y, or something like this. And you'll be told that, okay, this is satisfied for every single x and y in like this set in R, and you want to find all functions that satisfy this. So for this functional equation in particular, a function that works is, I think, just the identity function, which is f of x equals x for all x. This works, right? Why does this work? Because we'll check by substituting the function in. So the LHS becomes x squared plus f of xy, but f of xy is just xy. And the RHS becomes x times f of x, which is x plus y. And this is also x squared plus xy. So yeah, this works. And this works for every single value of x and y we can put in. So it's a function that works. But again, we're asked to find all functions. So we can't just stay there and we can't just say, okay, f of x is equal to x works, and that's it. We have to prove that f of x is equal to x is the only solution, or maybe it's not the only solution. It might not always be the only solution. So yeah, that's what a functional equation looks like. And the first thing we need to know about functional equations is someone asking a question in the chat. Okay, f of x is equal to 0. For this one, yeah, for this one, f of x is equal to 0 actually doesn't work. But I mean, yeah, it's a good spot if it were to work. But if you look at it carefully, wait, no, it does work. It does work. Sorry. Yeah, so I'll tell you how it works. So good spot. If you put in f of x is 0 here, then you'll note that, okay, this whole thing, it has an f outside of it, so it has to go to 0, right? And over here, f of x must be equal to 0. And 0 times whatever this thing over here is, it's going to be 0 times question mark. This is also 0. So 0 is equal to 0, which always works. This is always true. So we have found two solutions to this. F of x is x for all x in R, and f of x is 0 for all x in R. So we'll not look at this example for too long. How are you substituting value in LHS? I'm not substituting a value. Okay. Wait. How can I copy? Okay, I think. Okay. So what I'm doing is, I want to check that f of x is equal to 0 works, right? And if f of x is 0, then I know that f of this thing, like f of x squared plus f of xy, f of this thing will also be 0 because it's some x, right? Maybe I should say f of z is 0 for all z. Maybe the z and x is what's causing the confusion. But if this is z, then f of z is 0. In general, this will always be 0 because f is identically 0. No matter what value this takes, it will always be 0. And similarly, this will always be 0. And this will always be 0. So what we have is 0 is equal to 0 times y, which is 0. So it always works. How? Which part is the LHS? The LHS. Okay. So let's say we have, this is R and this is R. And we have a whole lot of values in R. And what our function is doing is, the mystery box function, what it's doing is it's taking every single value here, every single value, and it's sending it to 0. Every single value is getting mapped to 0. And since this is also a value in R, this has to be a value in R, right? Right? because this is in R, this is in R. So this thing is in R. No. No about which part? Okay. Yes. Okay. This thing is in R, right? And since that thing is in R, we know that f of that is also f of that will be 0 because everything f sends everything to 0, right? Okay. Yeah. Right. But yeah, I mean, you're not going to have something which is like, okay, this is not in R. It will always be in R. Every expression is going to be in R because R is whatever, unless we have a function like, okay, f of f goes from R to C or something where C is complex numbers, then this might not be in R, in which case the function would be undefined, like the thing would not be defined at all. X is R, but how is x squared R? R is the real set. R is the set of real numbers. And we know that, oh, no. Okay, I think there might be some sort of confusion. F of x is like f of x is 0 no matter where the x in R, where the x is in R. We don't care about where the x in R is. It is always going to map to 0. I mean, 1.1 squared is also in R. 1 point like pi squared is also in R, right? We can't square a real number and end up with a complex number or something, right? They are different values, right? Oh, okay. So the function, what the function is doing is the function is f of z is equal to 0 for all z in R. So the function is always sending any value, no matter what value it takes, it will send it to 0. Regardless of whether it's 1 or 2 or whatever. So yeah, I guess that is what the problem was. The function is f of z is 0 for all z in R. The function is not f of x for this particular x. The function is f of z is 0 for all z in R. So f of this is 0, f of this is 0, f of this is 0. So yeah, 0 times 0 is 0. So that works. So we'll not look at this functional equation. I hope that's clear. Yeah, you can also unmute. I'm fine with if you unmute. But I'll check the chat pretty regularly. So yeah. So let's move on. I'll now talk about, yeah, so in a functional equation like this, where we have now obtained, well, f of x is x works, f of x is 0 works for all x. What our strategy will be to show that they're the only solutions. The first thing that we should do is we should substitute some values in. So what I mean by substituting some values in is, okay, so let me find, okay, let's just do it here. Why not? So what I mean by substituting things in is, I'll copy the function equation. Yeah. So what we'll do is, suppose we let x is equal to 0. The functional equation should still hold then. It's not going to stop holding if I plug x is equal to 0 in. No matter what I plug in, the functional equation is still going to hold because it's an identity. Right? It's an identity, it's always going to hold. So I can plug in x is equal to 0. This is what I will call substitution. And I let y be equal to y. So y is still some variable. And what that gives us is f of 0 plus f of 0 times y. This is equal to f of 0 times f of 0 plus y. Right? And we have to find f of x, right?
To remove that
yeah,
extra term, it would be nice to put y as 0 also. When we expand, we get
What?
y f of 0. So to make it a bit nicer, we can probably substitute y for 0 also.
Oh, this is still pretty good.
F of 0. What?
I was saying this is still quite good. Like we can conclude some things from this itself.
Yeah,
Okay,
so
sure,
we
yeah.
can also substitute y for 0. It might remove the y f of 0 term.
In fact, I don't think we have to do that also. Like, LHS is f of 0, which is constant. So like
Okay.
RHS also has to be constant, and the only way for that is if f of 0 is 0.
Okay. Okay. So what? Whoever said that? Yeah, that's right. So this is constant, right? And this is also constant. But y is variable. And the only way y can be variable and these things are constant is that this thing also has to be constant, right? Okay, so what I'm saying is y is equal to f of 0 squared. No, y is equal to f of 0 minus f of 0 squared over f of 0, right? But y is variable, so this can't happen. But the only way this can't happen, like this literally can't happen, is when f of 0 is 0, because then this thing becomes undefined, right? And that's the only time this thing becomes constant. If f of 0 is say 2.5 or something, then we get 2.5y is some constant, which is not happening. Like we'll choose y is equal to 1 and y is equal to 2, and we'll get 2.5y is 2.5 and 5, which is not constant. This is a variable, right? So f of 0 is 0, and this is for sure. We know this for sure, and this agrees with both of our functions. One of our functions was f of x is x for all x, and the other of our functions was f of x is 0. So this is fine. This is all well and good. So okay, now we have f of 0 is 0, and this was our original substitution. Now let's try making another substitution. Let me copy the function. No, wait, I have copied it. Okay. Can someone suggest another substitution?
Letting x be x and substitute y for 0.
Okay, cool. So x is x and y is 0. So also for the sake of conciseness, please explain why f of 0 is 0. Okay. So f of 0 is 0 because when we plug in x is 0 and y is y, we get this. This is clear, right? F of 0 is equal to y f of 0 plus f of 0 the whole square. I mean, not the whole square, the square. So here, f of 0 is constant, f of 0 squared is constant, right? So what we have is y f of 0 is some constant, but y is right. Y is variable, but y times something is constant, and we know. I mean, it should be clear that if f of 0 is anything apart from 0, then y f of 0 cannot be constant when y moves around, because y can move around like 1, 1.1, 2, 2.5. For any value apart from f of 0 equal to 0, this will break immediately. You just take two different values of y, and y f of 0 will not be constant. So f of 0 has to be 0. I hope that's fine. Okay, cool. So yeah, f of 0 is 0. And for the sake of conciseness, what we'll do from now on when we write our substitutions like this, we'll call it p of some x comma y. We were substituting x for x and y for y. So this substitution will denote by p of x comma 0. And what this substitution gives us is f of x squared plus f of x times 0. This is equal to f of x times f of x plus y. Sorry, f of x plus 0. Yeah. And this expands out to, we know that x times 0 is 0, and we know that f of 0 is 0. So this will just be 0, and this is 0 anyways. So we get the equation f of x squared is equal to f of x the whole square. Cool. Okay, interesting. And what do we get? Does this give us anything? F of x is plus or minus x. Where did we get that from? Why do we have that? F of 1 is 0 or 1. f of 1, okay, so f of 1 is f of 1 the whole squared. When we plug into this equation 1, sorry, f of 1 is f of 1 the whole squared. So f of 1 is 0 or 1. Okay, sure. So yeah, okay. Let's not continue with. I mean, someone wants to, they can. If they don't want to do like more theory or something. Yeah. Hello.
I have a doubt that why did you take f of 0, why did you take the value of f of 0 is equal to 0? If we take the value of f of 0, then we can also take the value of f of x is equal to x. So why did you substitute the second answer only, f of x equal to 0?
Where? No. Okay. So what we got here is we didn't get f of x is 0. We got f of 0 is 0. So what we did is, did you understand this part? By f of 0 is constant, so f of 0 has to be 0.
Yeah, understand.
Right? F of 0 is 0. And this always goes to 0 no matter what. Did you get that?
Your voice is
Oh, my voice is. Oh, okay. Wait. Okay, I'll turn off my camera for a bit. Let's see if that helps. Can you hear me now?
yeah, it's fine now.
Okay, cool. So yeah, 0 always goes to 0, no matter what the function is.
Okay.
Right. What we did here is we substituted x is x and y is 0. Because the equation is an identity, we can substitute whatever we want in it. It will remain true. So we substituted y is 0. Right.
Yeah.
And we got x squared goes to x squared. X, y, what we're doing is we're replacing y everywhere with 0. Right. Because y is a variable. We can do whatever we want with y. The equation will still remain true. It will be weaker. It will be weaker, yes. But it will always be true. So y goes to 0 here.
I got it.
Okay, cool. Yeah, sure. So yeah, so this becomes 0, this becomes whatever, and f of x squared is f of x squared. And yeah, we continue on like this, and eventually we'll have some solution or the other. We'll have that, okay, these two work, these three work, whatever. And yeah, we'll be done. So before we continue with this, or before we try this again, maybe later. Also, yeah, I saw the chat. F of x is plus or minus x. I don't see why that's true. And point-wise stuff to work out. Okay. Yeah, we'll get there. Yeah, we'll get there. Okay. So we'll look at a very simple functional equation now. And this functional equation is going to be f of x plus y is equal to f of x plus f of y. And we look at this from naturals to naturals. So what can we say here? Okay, f of x is kx and y.
Basically linear function.
Can you please define the first?
Okay, wait, no, not linear. It will be f of x is k.
Kx, okay. Cauchy, okay. Yeah, okay. So this is called Cauchy's functional equation. I heard a doubt. I didn't hear what the doubt was, but I heard a doubt.
Can you please define the notations first?
Which notations? N means natural numbers. I defined this already. And natural numbers are just 1, 2, 3. Yeah. No zero.
The colon.
The colon. Oh, the colon means that the colon just means that the domain is n. The domain means the values that the function will take, and the codomain, which means the values that the function will output, that is also n. So the function is going from n to n. The colon doesn't really mean anything in particular. Okay, cool. pointwise trap where Cauchy functional equation. Yeah, Cauchy functional equation. Yes, this is called Cauchy functional equation. And as a lot of people have pointed out, the solution is f of x is equal to kx for any constant k, where k is in naturals. So any constant k, it works. Assume f of 0, n does not contain 0. N unfortunately does not contain 0. So yeah, what probably is meant by that message is f of 1, assume f of 1 is k, right? And what we'll do is, so we have f of 1 is k. If we put in 1 for x and 1 for y, what we'll get is f of 2 is f of 1 plus f of 1. And this is k plus k, which is 2k. Great. And now if we want f of 3, we have f of 2 plus f of 1. Right? I hope that's clear. This is like, we'll call this property, we'll call it either Cauchy or we'll call it additivity. Usually additivity, I like to call it additivity. But yeah, by additivity, we have f of 3 is f of 2 plus f of 1 because 2 here and 1 here, 2 here, 1 here. So yeah, we have this, and this gives us 2k because we've already obtained f of 2 is 2k plus k, which is 3k. So in general, we can see a pattern, right? F of 1 is k, f of 2 is 2k, f of 3 is 3k, and as expected, f of 4 is going to be 4k, and f of x is going to be xk. And people are saying induction, but I mean, people might not know what induction is. So I guess we'll just go with the pattern. So yeah, I mean, it is pretty clear what's happening. F of x plus 1, if we let x be x and let y be 1, f of x plus 1 is f of x plus f of 1, right? Because x 1, x 1. And this is going to be f of x minus 1. We're expanding f of x now. It's going to be f of x minus 1 plus f of 1 plus f of 1. This is the expansion from this. And so on and so forth. We'll eventually get f of 1 plus f of 1 plus f of 1 plus dot 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 plus f of 1. This is going to appear x plus 1 times. So, I mean, probably should have not done. Okay. But yeah, this is going to be x plus 1 times f of 1, which is k. So f of x plus 1 is x plus 1 times k. Or rather, it's equivalent to say that f of x is x times k for all x. And we can see that all of these functions work. So an important thing to check when we are solving functional equations is to check whether the functions we are obtaining actually work or not. So in this case, yes, we have kx where k is constant. So if we plug this in back, we get f of k, f of x plus y. This we want to be equal to f of x plus f of y. And since we claim that the answers are kx for any k, we get k times x plus y is equal to k times x plus k times y, which is 2, because kx plus ky is kx plus ky. K is not a function, k is a constant. Yeah. So kx works and kx is the only solution. So cool. That's a very nice solution. It's not as nice or something as, like, it's not unique. It's not only f of x is x. But yeah, this is fine. This works. It's not bad. But now let's move on to rationals. What happens if f goes from q to q? And we ask the same question. F goes from q to q. Q are the rationals. And we have f of x plus y is f of x plus f of y. Does someone want to guess what the solutions are for this? Or maybe just not all of the solutions, maybe some set of solutions or something.
It'll be the same.
Yeah, okay. So kx works. This kx works. And kx works again because, and of course here k is in the rationals. So all k, f of x is equal to kx for all k in rationals. where k is some constant. So basically we are saying that x, 2x, 1.5x, all of those functions individually, they work. And this is true because again f of x plus y is kx plus y, f of x is kx, f of y is ky, and yeah, okay, cool. So they work. Where are the only solutions? Why checking that the function satisfies the functional equation is necessary? Okay, so basically what we have is, how do I say this? Okay, so suppose we get, okay. So suppose we get for a function, we get f of 0 is 0, and we get for some function f of 0 is 0, f of 1 is 2 or 3, and f of 2 is 7, f of 3 is 9 or 11 or 13 or something like this. So we have some sort of characterization for all of the values, but not all of the values might work. So we might have something like f of x squared is equal to, no, what? Yeah, f of x squared is x squared we might have, but this is not a complete characterization, right? Functions, basically what we are saying is, what I'm trying to say is, f of x squared is equal to x squared. The functions that satisfy this can have the value of f of 1 to be 1 or minus 1, because f of 1 squared is going to be 1 squared or minus 1 squared, and they're both going to be 1 in the end. And f of 2 can be 2 or minus 2, but it can also be something like f of 1 is 1 and f of 2 is minus 2. Right? It might not always be f of 1 is 1 and f of 2 is 2, or f of minus 1 is, sorry, f of 1 is minus 1 and f of 2 is minus 2. So when we are given something like this, we can't just say that all such functions work. So it's important in the end to check whether the functions we've gotten work or not. What we have is, okay, yeah, so we have some functional equation. We are obtaining reductions from this, right? But this is only one way. We know that, like, if the functional equation works, then this works, right? This is possible, but we don't know whether it actually works or not. This is possible, but we have to plug it back into check. Okay, anyways, that's probably not the best explanation. That's probably a terrible explanation, but yeah. Anyways, yeah, so this rational thing, how do we do it? Any ideas from people who have not seen this before, maybe? Come on, any sort of ideas, any substitution.
Yeah, like if it is a half integer, like if it is n by 2, then f of n is just f2 into f of n by 2, and then I think generalize.
Okay, so you're saying f of n by 2 plus f of n by 2, this is f of n by 2 plus f of n by 2, which is 2f of n by 2, and this is f of n. Okay, cool. So in general, what we actually have is, again, if we take f of 1 is k, then of course for the integers we still have, yeah, for the integers we will still get f of x is kx, simply as an extension of what we've already done. We've already shown that if it holds over integers, then it's going to be f of x is kx, right? So f of x is kx, but f of 2, no, not f of 2, like suppose we have some f of 1 over 2, then from this we know that f of 1 over 2 is going to be k over 2, right? And in general, when we have f of p over q, what we're going to get is f of p over q plus, okay, so p over q, by p over q here I mean, like, assume whatever, like it's in primitive form, like p and q are co-prime and they're both in z, right? So it's some z divided by some z. So what we get is f of p by q plus f of p by q. This is going to be f of 2p by q. And when we add f of p by q to this is going to be f of 3p by q, right? And so on and so forth. Q times. Yes, q times, exactly. So what we get is, if we add f of p by q to itself q times dot 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 f of p by q times, then this is going to be f of 2p by q, f of 3p by q, f of, in the end, f of qp by q. This is just f of p. But p is an integer. P is an integer, right? Because p is the numerator of this. So this is pk. And this side, it is, what is it? Q times f of p by q. So what we get is f of p by q, for any p and any q, it is going to be p by q times k, which is what we wanted, right? Which is, we wanted f of x is kx, and we've gotten that f of p by q is p by q times k. And again, checking, we already checked, it works, right? So for the rationals as well, this is the only solution, kx. For any rational number q, kx. Sorry, for any rational number k, f of x is equal to kx, it works. Cool. And now, what's next? Well, can someone predict what I'm going to do next?
Reals now.
Yeah. So we went from integers to rationals, and now we'll go from rationals to reals. How are we going to do this?
You just don't do this because it's really hard.
Because
It's really hard. I mean, there would be many solutions.
Yeah, the
Okay.
issue is that we could, in the previous one, in the rational thing, we could convert rational to integers. In the reals, we cannot do that. Or at least it's extremely hard.
Okay. So basically, yeah, that's correct. So f of x is kx again works here, right? For k in reals.
But this is only when it's continuous.
Yeah, okay, exactly. So f of x is kx still works for k in reals, but it's not the only solution. And I'll try to briefly explain why it's not the only solution. So suppose we have something like square root of 2, right? Square root of 2 is in reals. We are expected to find some value of square root, some value of f of square root of 2. So, and we are expected to obtain this value of f of square root of 2 from this equation, f of x plus y is f of x plus f of y. But unfortunately, we know that square root of 2 is irrational, which means we cannot obtain it from rational additions. No matter how many rationals we add, no matter how many rationals we subtract, we can't get to the irrationals in any way whatsoever, right? Because q plus q for q in rationals, it is going to still be in q. So square root of 2 we just can't get. But okay, sure, we can't get square root of 2, that's fine. But what we did last time was we assumed f of 1 is k, right? We need some entry point. So okay, sure, I'll assume f of square root of 2 is some m, why not? But then what we'll notice is, using addition and using all of these square root of 2 things, like using all numbers of the form a plus b times square root of 2 for a in q and b in q, this is still not enough to get square root of 3, right? No matter what we do, we won't get square root of 3. So okay, we'll give another variable, we'll give L. But then we'll notice that, oh, this is never going to end. This is just never going to end, because eventually we'll realize that, okay, the square roots are not even the only thing. We have pi, we have e, we have all of those transcendental numbers. So we're not getting anywhere. So this equation, it has a lot of solutions, a lot of really bad solutions even, because we can give literally any value to m, L, and these infinitely many irrational and transcendental numbers, right? We can give them whatever values we want, and we'll get infinitely many solutions. So yeah, this is not going anywhere. But fortunately for us,
could you tell one solution which is not of the form of x equal to kx to this.
Not equal to kx.
Yeah, like no, can you like tell a non-linear solution to this?
Okay. I mean, that's what I just described. Like, this is a description of a nonlinear solution where you have infinitely many things. But to be particular, let's say uh, I mean, see, the thing is, all the functions that are going to be like that, they're going to be piecewise. By piecewise, I mean we'll have some description for this and we'll have some description for this. So I can give you some really scam solution like f of x is kx for everything like x in some set, and I can tell you, okay, f of a plus b root 2 is equal to
something else and
exactly,
like,
yeah,
then
exactly, yeah, ak plus b square root of 2 times l. So if this set is everything excluding numbers of the form a plus b square root of 2, and this set is everything of the form a plus b square root of 2, I can define things piecewise like that. So yeah, the solutions are really bad. But fortunately for us, I will not prove this here because yeah, we have barely any time. But yeah, so what we have fortunately is that if we are given specific conditions on f beforehand, in addition to this, then we can say that oh, f of x is always going to be kx, and those conditions are f is continuous, or f is monotonic. I'll explain what these terms mean in a second. Or f is these are not like the only conditions. You can have some variations of these as well. Continuous, monotonic, bounded. So I'll explain what these mean. Continuous means that we can draw f on the xy plane, or like whatever. What is happening? I mean, not on the xy plane in particular. I mean, what do you call it? Like this is x, this is f of x. Let's say. Then we can draw it continuously. There is no gap. That is what it means roughly. And monotonic means that f is always either strictly increasing or strictly decreasing. So the graph looks like this basically, or the graph looks like this. And there can be gaps here. It doesn't need to be continuous for the condition because monotonic doesn't mean continuous necessarily. It can be like this, whatever. And bounded means that f will not take any values above a certain point or below a certain point. Like it can be like this, it can be like this, whatever. I don't care. I mean, not intersecting, of course, but like this, like this. But it's either bounded above or bounded below. There is some value which it won't take a value, which it won't give f of x is lesser than m, or maybe it won't give f of x is greater than m for some value.
But
So,
kx isn't bounded, right?
Yes, kx is not bounded.
So it is not a solution.
Oh wait, no.
F of x
So,
by x is bounded.
sorry, I didn't mean f is bounded. I meant like, I mean I did mean f is bounded, but okay. So how do I explain this? Okay, so what I mean is, of course, in f going from r to r, kx is not bounded, right? Kx is not bounded, but kx is continuous and kx is monotonic. So I don't mean to say that all three of these conditions must hold. Any one of these conditions holding is sufficient to say that f of x is going to be kx for x. And so by bounded, I'll give an example of what I mean. If f goes from r plus to r plus, right, and f of x is kx, sorry, f of x plus y is f of x plus f of y, then the values of f are going to always be greater than 0, right? And this is what I mean by bounded. It's non-trivially bounded for a certain value m, and it's always going to be greater than that value m. So for r plus to r plus, I can conclude that f of x is always going to be kx. Also by r plus, I mean like reals that are greater than 0, right? So if this set is already bounded on its own, so if it's going to be like r greater than 2 or r greater than 4, or r less than 2000. If this set is already bounded, then I can definitely say that I can definitely say that f of x is kx. I hope that's clear. I haven't proved this. I will not prove this. But okay, does this imply all three or one of them? No, only one of them is fine, right? Because there are functions which are continuous but not monotonic. There are functions which are monotonic but not continuous. There are functions which are bounded but not continuous. There are functions which are bounded but not monotonic, and so on and so forth. Yeah. Oh, cool. So we'll actually look at a problem now after all of this. Actually, should we actually even look at a problem? Okay, let's look at something before we look at a problem. More theory. And what we'll look at is the concept of injectivity and surjectivity. So suppose we have R, and we have a mystery box function, and f is taking values from everywhere, and f is outputting values everywhere, right? So some really nice properties to have for an f would be a property I'll call injectivity. I mean, I'm not calling it that, it's just universally called that. But yeah, injectivity, what injectivity means is that no two values, say
Of domain.
x and what? Hello? So by injectivity, what I mean is, if I have two values here, then they're not going to output the same value through f, right? So for example, a function like f of x is equal to x, this is going to be injective, because if I have f of x and if I have f of y for x not equal to y, they're always going to map to different things. One is going to map to x, one is going to map to y, right? So this is what I mean by injective. Similarly, f of x is equal to kx, that is also injective. F of y is equal to ky, and these two are never going to be equal unless x is equal to y.
Can you repeat the injectivity again?
Okay, so what I mean by injectivity is that for two different values x and y, the function is not going to send them to the same value. So f of x is not going to be equal to f of y for x not equal to y. So for a function like f of x is kx, right, we will have f of y is ky, and these two outputs are not going to be equal. Kx will not be equal to ky, unless of course k is equal to 0 or x is equal to y. So I should probably clarify what I mean by k is k not equal to 0. So this function is injective. All right, I hope that's clear. And what I mean by surjectivity now, surjectivity means that this set, the codomain, is covered in its entirety. So all values in codomain.
Typically, codomain is the range.
Yeah, codomain is the range, or codomain is the image, whichever way you want to say it, are achievable. So if I have something like f of x is kx, then it is surjective, because if I choose x is x by k, then this will be k times x by k, which is equal to x. So all values of x are achievable if I plug in x by k. Again, k is not equal to 0. But if I have something like I'm going from n to n, and my function is f of x is kx, right, then this is not surjective. Why is it not surjective? Onto function. Yes, I think this is called onto and one-to-one in like alternative things. Like injectivity is called one-one, and surjectivity is called onto, I think. Yeah.
This
Sure.
would
Why
be
is
subjective if and only if like k is not equal to 1.
what? Can you repeat that?
It's
This
the
would be
opposite.
subjective if k is equal to 1, else it would not be subjective.
Yes, exactly. if k is not equal to 1, then what we have is, if we have k equal to like say 4 or something, then the problem would be that f of x,
multiples of 4.
yeah, f of x would be multiples of 4, which is not the whole set M, right? But if k is 1, then it would be multiples of 1, which is the whole set M, because every number is a multiple of 1. So, okay, good, amazing. So now we have defined injectivity and surjectivity, and I hope that's fine. And I'll define one last thing, like just one last thing. So odd and even. What does odd and even mean? By the way, not all functions are going to be injective. I mean, or surjective. Like there are functions that are both injective and surjective. Those are called bijective functions, and there are functions which are neither injective nor surjective, and those are just functions. Those are just functions here. So odd and even. This is another categorization of functions. Odd means f of x. This is equal to minus f of minus x. No. Yeah. F of x is equal to minus f of minus x. Or I can rephrase this as f of minus x is equal to minus f of x. Yeah, this is just a this is just a ease of access thing, because I don't want to say. Yeah, okay. So can someone give me an example of an odd function? Okay, no, I'll give an example of an odd function. Yeah, odd function like 5x or x or 2x or like whatever. A lot of functions are odd. What is the example of an even function?
Cos x.
X squared.
Okay, cos x, sure. I'll go with x squared.
Any polynomial in x squared.
Yeah, any polynomial in x squared. Very good. So any polynomial in x squared, what is meant by that is basically all the exponents are even. So x and minus x, no matter what we put in, it's going to give the same thing. It's going to give the same output. So f of x is equal to f of minus x, and the function will be even. Okay. Yeah, so that's odd and even. Now, okay. One more thing, just something to remember. When you have some functional equation, make sure to not assume like you have some f of this plus whatever. Make sure to not assume in your thinking that f is polynomial, because f might not be polynomial. F does not have to be polynomial, right? F is a function. Cos x is not a polynomial. Sin x is not a polynomial. So if you want to verify, however, if you want to just check like what the solutions might be, then you can say, okay, I'm checking f of kx plus m, and you can check, okay, so k is equal to 1 and m is equal to 0. That works. I mean, you can plug in kx plus m. Sorry, what am I?
But like we can express cos x like as an infinite polynomial.
Yeah, but I mean, not even cos x. Like there are infinitely many other functions which are not polynomial, right? I mean, we are not looking at infinite expansions. We are just looking at polynomial in finite, yeah, polynomial in finite terms or finite degree or whatever. Not finite degree, yeah, just finite terms. So yeah, f of x is equal to kx plus m. You can assume this just for like your internal checking of what the solution is. So maybe you plug this in and you get k is equal to 1, m is equal to 0. So you know that out of all kx plus m, only f of x is equal to x works. But you don't know this for all of the functions that exist. You only know this for all of the kx plus m, right? So yeah, don't assume implicitly that f is polynomial. Okay, so enough theory, and I should probably do some problems so it will be clear. And I have to look at some tricks. Can you repeat odd even through graph? Odd even through graph. Okay, so what odd functions will look like is like they're going to be symmetric. They're going to be reflections about this, I think. Yeah. No, they're going to be reflections about like there's going to be reflections about like the origin or something, because like this is going to be equal to this. But even functions are going to look like, if you have this, then it's going to be like over here also it's going to be this. So if you have this, it's going to be like this. This is even, this is odd. Yeah, the reflection, even is reflection about axis.
We can say that like for odd function there is a rotational symmetry. Like if we rotate it, we'll about like 180 degrees, so we'll get the same thing.
Yeah, I mean it's a reflection about the origin.
Yeah, so like is it that the same thing?
Is it?
It's not always the same thing, right?
It's not always the same thing. Like if this is theta and this is wait. What do you mean by rotational symmetry? Oh,
Like
if you rotate it by 180 degrees, then it's the same thing, you're saying.
yeah,
Is that true?
Yeah, I
yes,
don't
because
think that's true.
since x comma y maps to minus x comma minus y, so we can say that if we rotate it, minus x comma minus y would just be again x comma y.
Yeah, that actually has to work.
So that
Yeah.
should be good.
Oh wait, I was thinking of. Okay, yeah. Fine. So rotational symmetry or like reflection about zero or whatever. Yeah, so that's the graphical interpretation, I guess. Okay, now we'll actually move on to problem solving strategies. We're probably not going to get time to actually look at problems per se, but it's fine. It's fine. Okay, we'll look at one problem really quickly, and then we'll actually look at some cool problem solving things. Oh my god. Oh my god. What is this? Okay. Okay, so really quickly, what substitutions can we make? Zero. What happened till now? A lot of stuff. We looked at injectivity, surjectivity, some definitions, what a function is, etc. etc. But yeah, I don't know. It's not true. Not true. Not true. Yes, it's not true. It is true. It's not true. Okay, cool. Okay, so I'll just okay. So in general, for a functional equation like this, what you want to do is you want to substitute zero first of all.
Yeah.
Especially when you're given r at least, because
Yeah.
you're given r, substitute zero. So let's
Also, x equal to y gives f of 0 equal to 0.
okay. So
Yeah, sure.
again, I'll denote by p of x comma y the assertion
Assertion.
x and y. So p of x comma 0 first, it gives f of x squared is
X
x
of
f of x. Okay.
uh,
P of 0 comma 0, someone said. It gives f of 0 is 0, which is clear from here also. We can put x is equal to 0 and we'll get this. F of 0 is 0 and f of x squared is x times f of x.
we could try f of 0 comma x. That would like give
Okay.
x kind of
0 comma x. This gives us f of minus x squared is
equal to minus x.
Combined
So
with
this
this,
is enough to assume that it's odd, right?
No, why? Because like this is only x squared can only take positive.
Yeah, but it doesn't really matter, right? If you want negative, just take minus of positive.
exactly. Wonderful. So yeah, x squared is x f of x, minus x squared is minus x f of x, and minus x squared is minus f of x, x squared is f of x. Like both ways, it's minus of each other. So f is odd. Yes. And also, for any odd, yeah, wait 1 second. So yeah, for any odd function, by the way, by definition of odd, what we have is f of f of 0 is going to be minus f of 0. So f of 0 will be 0.
Yeah.
And we can look at that graphically too or whatever, because like we know that it's reflections about 0. So the reflection of 0 will be at 0, because if it's here and here, it's just like there won't be any value for 0 or whatever. Yeah, sure. So f of 0 is 0. And
now we could just substitute p of x, p, we could look at p of y comma x and p of x comma y simultaneously.
okay, so what you're saying is we are looking at p of x comma y, which is just this equation, and p of y comma x, which I'll write underneath this, which is y squared minus x squared is equal to y f of y minus x f of x. What does this?
So like kind of proves it is odd.
Exactly. When we sum this up, we just get that result. So okay, doesn't matter. Fine. So what do we know? We know f of x squared is x f of x. We have x f of x here, right?
So we should
So
try to make one of the one of the functions same.
Wait, don't we have Cauchy's kind of now?
yeah, exactly. So what I'm saying is f of x squared minus y squared, we get that this is f of x. Okay, yeah, f of x squared minus f of y squared, and this is kind of like Cauchy's, right?
Cauchy, yeah.
This is kind of like Cauchy's. Can someone show that it is actually Cauchy's?
What?
I mean, like, it is. It looks like Cauchy's, but for Cauchy, like for it to be completely Cauchy, what we want is this can go throughout reals and this can go throughout reals. But this is like positive, right?
Isn't it implied by since f is odd? So we can just do that.
What?
It is obvious now. It would be Cauchy since like f is odd.
Exactly. So this minus is basically just like you can substitute minus here or whatever. Like you can take this here, take this here, and you will get minus values as well. So it takes a little bit of work, I think, a little bit of thinking, but you can reasonably conclude that yeah, f of x, f is Cauchy. But then what?
But we
We
can't use that since like f might not be continuous, bounded, or that monotonic.
yeah, sure. We can't. But what can we do? Suppose from here we have gotten that f of x plus y is f of x plus f of y.
Maybe substitute x to minus x in this. Okay, well, that would make sense.
Actually, I'm not sure if this is direct from here. It actually might take a bit of work, I think, because these are all dependent on each other. I'm not sure if can you conclude directly.
We just have to prove that.
I mean, it's fine, sure. I mean, because we can't really do anything with Cauchy anyways. So let's just work with this, substitute values into this, because
No,
does it
put
really
x. Can't we plug x squared equal to x squared plus y squared? Like just to make things look nicer.
x squared is equal to x squared plus y squared? Yeah,
How
sure. Why not?
about if x is equal to x plus 1 and y is equal to x?
Okay, let's do things one at a time. So one suggestion is x squared is equal to x squared plus y squared. Yeah, okay.
Excluding the variable overlap. Yeah.
Yeah, I mean, sure, I'll do z squared plus y squared. Why not?
But that is only when like you can assume x square equal x square plus y square only when x is greater than y.
Yeah, exactly.
Not x is greater than y, not y, I'd say.
So I mean, this is a thing, but this is kind of weaker. And so the other suggestion was x plus 1 the whole squared, and y is x squared. Y is x, sorry, and this is x squared, and this is equal to f of x plus 1 the whole squared. So, okay, my handwriting is getting progressively worse, but it's fine. What does this tell us? This tells us f of 2x plus 1 plus f of x squared is equal to f of x squared plus 2x plus 1. Okay, the graph is correct. Oh, what? There is some sort of lag going on. I'm not sure. What? Why are my chart? It's 7:13. My computer shows it's 7:10. What's happening? Okay. Anyways, yeah. So f of 2x plus 1 plus f of x squared is f of x squared plus 2x plus 1. What does that mean? Does that give us anything?
By the way, f is like injective, right? I think.
Injective. Why is it injective?
We had f of x squared is equal to x f of x, I think.
F of
So
x squared
if
is x.
okay, no, it is not. It might not be. Okay, yeah, probably.
Exactly. Ideas. I'll go down. Okay, the screen is lagging. It's fine. If you have any doubts, feel free to ask. Completely fine. Don't getting anything. Wait, do you mean like not getting anything as in like the topic, or like not getting anything in the problem? Topic. Oh, okay. Like, feel free to ask anything you're unclear about. Okay. Ideas.
Can we just substitute x squared as just a positive real for now and use that x square is equal to x square is equal to 1 minus, sorry, y square is equal to 1 minus x square, because then you can get f of 1 and something like that.
What?
Can we substitute y square is equal to 1 minus x square?
Y squared is 1 minus x squared. Okay, sure. Y is 1 minus x. I mean, might as well do x minus 1.
Right. So we can substitute x is we can assume x is positive and maybe work with that.
Why do we want to assume x is positive?
No, like I'm saying y square is equal to 1 minus x square.
That's what I did.
No, I don't mean y is equal to 1 minus x. I mean y
is equal to 1 minus x squared.
Yeah.
Okay. So I mean that would need x is less than 1. Equal to, less than equal to.
Right. I was thinking if you'd assume that maybe something, but yeah.
Okay. Sure.
We like make one side of the variable of the equation like constant and the other side vary somehow.
Constant. Which side? Where? I mean, okay, sure.
I also don't like how, but
Uh, okay, how about this? We know f of x squared is x f of x. Right?
Can we do this like f of x square is x of x? So f of x square by x square is f of x by x. So let's define g of x as f of x by x. So we kind of get that g of x is constant.
Okay, wait, repeat that again.
Like f of x squared is x of x.
F of x squared is x of x. And now?
Divide by x square, both sides. So
How do we get that g of x is constant?
like I said, almost constant. If you assume f of x by x is dx.
I mean, sure. This is not almost constant. G of x is equal to g of x squared. Cool. Okay, fine. So what we'll do here is, can someone? Okay, is there something that you can get with Cauchy? Cauchy is not hard to show. Cauchy just requires a little bit of work. Like you have one thing is positive, one thing is negative, or whatever. But it's also everything works out nicely. So we have Cauchy. There's like
If we can get that positive maps to positive, then like we would be able to use Cauchy, right?
No, we don't need that. Like we do have like negative things. Like we have f of x squared plus f of minus y squared is equal to f of x squared minus y squared. But that just means we have one thing is positive, one thing is negative is equal to like the sum of that. And we can like switch things around. We'll be fine without.
Monotonicity, perhaps?
We don't have monotonicity.
Can you like
Okay.
attempt to prove it?
How? Okay, so what we'll do here is we have additivity. Additivity is really strong. And what I'll say is that f of x squared is equal to x f of x and f of x plus y is equal to f of x plus f of y. They are alone enough to give me what I want. And that is true
We can
because
do f of x plus 1 whole square. That will equal to x plus 1 times f of x. That will give f of x equal to x f of 1.
yes, true, correct, absolutely correct. So over here, if we plug in x plus 1, we get f of x squared plus f of 2x plus f of 1. This is equal to x plus 1 times f of x plus f of 1. But now we will note that, this is 2f of x. So x f of x, this is f of x squared, so it cancels out with that. And 1 f of x is f of x, so it cancels out the 2. And what we'll get in the end is f of x plus f of 1 is equal to f of x plus f of 1. What happened? What did I do? I see. Oh, yeah. Sorry. It becomes. Oh, it's f of 1, bro. Okay, sorry. It becomes x f of 1 plus f of 1. Like, I'm just expanding this, by the way. And I'm using x f of x is equal to f of x the whole square. Sorry, f of x squared. So, yeah, cancels out the f of 1. We get f of x is equal to x f of 1. And this does work. This does work. Again, remember to check. It does work. Because if I have kx, where f of 1 is k, then k times x squared minus y squared is equal to kx squared minus ky squared. If anyone is unclear about why this will imply f of x plus y is f of x plus f of y with odd, then you should work it out as an exercise on your own. It's not that hard. It's just a little bit of work. Not even a little bit of work. It's just using odd. Someone is okay. Okay, cool. I hope this is clear. We got f of x is odd, f of x plus 1. Yes. Yes, Ashwika is correct. Can you repeat the odd and even again? Okay, odd and even means if it's odd, then f of x is minus f of minus x. If it's even, then f of x is f of minus x. So for x squared, what we have is minus 1 squared. This is equal to 1 squared, right? So x squared, and in general, minus x squared is equal to x squared. So x squared is even. But for a function like x cubed, we have minus x the whole cubed is not equal to x cubed, right? Because minus 1 the whole cubed is minus 1 and plus 1 the whole cubed is plus 1, and they're not equal. But they are negatives of each other. This is minus x cubed and this is x cubed. So they're minuses of each other. So they sum up to 0. And when they are minuses of each other, then the function is odd. So that's fine. F of 1 times x, yes. Is this correct? Yes. Perfect. Okay. So this was a basic example. We didn't really use much here. We used none of the injectivity, surjectivity here, but it managed to work out. So that goes to show that substitutions are really powerful. Additivity is really powerful. And additivity, most of all, combined with other things, sometimes it just gives you what you want. It just gives linearity. And finally, I'll just mention some tricks that are important. So functional equations is really a topic where it's like, how can we use odd, even, surjective, injective in questions? Yes. So to prove injectivity, usually what you do is, basically what injectivity gives is that if it's injective, then if we have f of a is equal to f of b, if we have something like this, then we can just cancel out the f's, right? Because if it's injective, then we know that if f of a is fb, then a must be b. So injectivity just means you can cancel out the f's. You can't do that otherwise. For example, if you have injectivity and you also have f of x is equal to f of x, then you can just cancel out the s and you will get f of x is x. That's what injectivity does. And surjectivity, what it does is, surjectivity, it allows you to say that I can assume there is some x such that f of x is c, where c is like, I don't know, 0, 1, 25, whatever, because any value of c is attainable for some value of x. So I can choose a value of x and I can put it in. Suppose I'm not getting that f of 0 is 0, right? But I have that surjectivity exists. Then I can plug in, well, y is equal to some x, y is some c, where f of c is 0, and then this becomes 0. So surjectivity is also really useful, if I have surjectivity, that is. And the way to prove injectivity and surjectivity, it goes something like this. Usually what happens is, you have f of a is equal to f of b, you assume this, and you also assume that a is not equal to b. Basically you are using contradiction, right? You do this, then what you do is you plug in, again p means plugging in or p means assertion, you plug in something like x comma a, and wherever a has gone, you plug in x comma b, right? And you somehow hope to show that a is equal to b, right? You somehow hope to show this, so a contradiction will be achieved and f will be injective. Or you can do like f of a comma y, you can do f of b comma y, etc. Right? So that's how injectivity is proven. Surjectivity is usually if you have something free, like you have f of x squared plus y squared is equal to y plus f of x, then what you can do is, you can say, well, I'll put this as constant, like x is 0, so this is 0. So what you get is f of y squared. You have this free variable, right? You have this free variable. So usually when you have a free variable, you will get subjectivity. Like not all of the time, but like you can hope to get subjectivity at least. Because now this is constant. Sorry, this part is constant, right? But I can move y appropriately. I can say y is now y minus f of 0. So what I'll get is f of y minus f of 0, the whole squared. This is equal to y. So all y can be achieved through this value of something, and I put the f on it. So this is how you prove surjectivity. Use of surjective again. Okay, so suppose you have surjectivity, then what you can do is you can assume that there exists some k, such that f of k is equal to some like constant. Suppose I want to say that, okay, like c is 0, right? So I can show that there is some value k such that f of k is 0, and then I can plug in k, like f of k comma x, and then f of k is 0. So like basically f of k just cancels out everywhere, and a lot of fun stuff happens then. X will still be x, but you can do something like maybe f of k comma k even if there is something going on, and this will probably may give f of 0 is 0, it may give some other thing. So yeah, surjectivity is also really cool, but injectivity is usually something nicer to have than surjectivity, not like degrading subjectivity in any way. It is also really cool. Anyways, so that's how you prove and use injectivity and surjectivity. I know I'm not giving any examples, but there's really a lack of time kind of. So maybe we can do an FEPSS in the coming weeks. And I mean, we'll get an FE problem set as well. So you can ask me any questions you have there. And we can do an FE, like the problem set, we can do a problem solving session from the problem set. But final notes, I'll tell you some problem solving techniques. This was all basically theory, right? I'll tell you some problem solving techniques. The substitutions you want to substitute in the functional equation, right? They can be really unmotivated at times. And the way you want to substitute is often really clever. And so I'll just mention a few tricks, right? The first trick is, okay, I mean, it's not a trick, but of course you always want to substitute 0 in first and 1 and all of that stuff. 0 and 1 are usually like very nice. You can substitute f of x, and this is really cool to substitute. I mean something like x, you are substituting f of x with f of x, or y with f of y. And this helps in functional equations where it's like you have two f's already, and you have something free over here, x plus 2, right? Then what you will get if you substitute x is f of x, what you will get is f of x. This is equal to f of x plus 2, right? But then also notice that this is f of x, but I know that f of x is x plus 2. So this in another way, this is equal to f of x plus 2. So what I've gotten is f of x plus 2 is f of x plus 2, right? So that's also really cool. So when you have two f's, you can put an f inside the x, like you can do f of x like this, and you will get some expression in two different ways.
But then for this, you need to have f as surjective, right? Or else it would be very weird to
No. You don't need to have f as surjective, because what I'm doing is I'm substituting x is f of x.
Okay, yeah. Got it.
Yeah, I'm not doing anything like I'm assuming f of x
Yeah.
is some value. I'm just saying that okay, this holds. I'm just saying this equation holds. So this is called the triple f trick in some places.
Yeah, but this might fail if if the codomain is smaller than the domain, right? So if we cannot put in f of x, so if we have a function from say real positives to all reals, then it might fail.
I mean, what do you mean by fail?
Fail like f of x won't be defined, right? Because it is real, but it is not real positive.
Yes. So what I'm trying to say is f of x is something that's given to you in the equation. Like you have f of x and you have something or the other. You have somethings here, and this is equal to something.
Okay.
In that case, it's really not going to happen. So yeah, I mean, of course, keep in mind what you're substituting in. But in general, when you substitute f of x inside here, f of x is going to be in the thing. Okay, regardless. I mean, sure, it's always a good thing to check whether it works or not, like whether you can substitute something in or not. But yes. R. Yeah, correct. So r plus 2 r. Yeah, if you have something like r plus 2 r, then definitely you cannot substitute. If you have just f of x, then you can't substitute f of x in here because f of x might be negative, right? So yeah, that's a great thing to point out. So be sure to check what you're substituting in. Of course, in naturals you can't substitute pi. If you have an equation on naturals, you can substitute pi. So yeah, that's the thing. This is one trick. Another trick is symmetry. So what I mean by symmetry is, suppose you have some equation f of x squared plus y squared plus 2xy is equal to f of x squared plus f of y, no, yeah, sure, f of y the whole squared plus f of 2xy. Then here what I have is, this expression is symmetric in x and y. This expression is symmetric. This expression is symmetric in x and y. But this is not. So what I can do is I can exploit the symmetry of these two things, this thing and this thing, and I can substitute y comma x, and what I will get is f of y squared plus x squared plus 2xy. This is equal to f of y squared plus f of x, but square outside, right? This is inside, this is outside, plus f of 2xy, right? This is the same as this. This is the same as this. So what you expect to have is this is the same as this. You don't expect, this is true. This has to be true. So this is going to be equal to this. So you get f of x squared plus f of y squared is equal to f of x squared plus f of y squared. In this case, it might not be so useful to have this, but in other cases, it might be really useful. Right?
You can still use it, right? You can take f of x the whole square, the LHS, and then f of, okay.
Yeah, I mean, what this gives over here is at least you get something like f of x squared minus f of x squared. This is constant for all values of x, because like what you get is this is equal to f of y squared minus f of y squared. So you get this is equal to this. So for all values of x, because you can substitute any y in, this is going to be some constant. So yeah, cool, fine, okay. So that's one thing. And the final thing, which is probably the most important thing, most important trick, this is going to be forced cancellation. Forced cancellation is amazing. Basically, you're telling two things to be equal and you're not even asking them whether they want to be equal. So probably best to give an example. Okay, I'll take a really quick example and then we'll end off the class. Where is ah, wait, just 1 second, sorry. But yeah, feel free to ask for doubts in this time, process what I've said. National and regional. Okay. I'm going a little bit over time, but I hope it's fine. This is a problem. Thoughts? Any thoughts?
Probably force x plus 1, the like
Yeah, the
double F cube.
RHS F should be equal to one of the LHS Fs, and then we get cancel and something is 0.
Exactly. So forced cancellation, what it means is you're going to force something inside of the f, right? You're going to force something inside of the f to be equal to something inside of the other f, and when you force that to be equal, these two things will go away, and you'll get f of y for whatever value of y you just put in. That is 0. So that seems really weird. So what do I exactly mean by that? So what I'm trying to force is xy is equal to x plus 1 times f of y. What does that mean? Well, this is free in some variable. This is free in x, because when I have y and f of y, I can't really force f of y to be something, right? So what I get is some value of x in terms of y. So I'll expand this. This is just solving this equation. So plus f of y. So f of y divided by y minus f of y seems like that's
Why couldn't we do the same with when we replace when we take I to the LHS,
when we take
y to the LHS rather than x?
okay. So I'll let's see what happens. Let's see what happens. So here y is on the LHS, right? So what we get is y is equal to x f of y plus f of y divided by x. But here y is not independent of itself, right? Y is calling itself in its definition. Y here, but we have f of y over here, right? So the problem is I can't substitute in a y which already depends on itself.
Same thing here. We have to make sure x is defined.
We have to make sure here.
Yeah, y minus f of y.
Exactly.
If that's
Okay.
0. So two cases.
Let's assume for now that y is not equal to f of y.
So yeah, that will give us two cases. We and then like we disprove one of them, and hopefully we get f of y equal to.
Okay, so basically what we are doing here is correct, sure. So y is not equal to f of y, let's assume. Then we substitute this x in, and what we will get is xy is equal to x plus 1 times f of y. So these two things are bound to be equal, right? Not by injectivity or anything. This is just straight substitution. Why? Because I'm not saying that f of a is equal to f of b implies a is equal to b. That is injectivity. However, a is equal to b implies f of a is equal to f of b. This is just true. This is just true, right? So what we get is if y is not equal to f of y, which is the condition for this substitution to actually happen, right? If y is not equal to f of y, then f of y is equal to 0. Because here I have this f of y, and this is the only term that remains after these two cancel out. So if y is not equal to f of y, then f of y is 0. Otherwise, like if f of y is not 0, then f of y is 0. Sure? Cool. So, okay. Now, I'll rephrase this as the contrapositive or whatever. F of y not equal to 0 means that f of y is equal to y. And this is what we want in life. We want that f of y is y. So we really want that f of y is not 0. So we want to find when, for what y, f of y is 0, so that I can try to eliminate those things or something like that. So now what do I do? Okay, let's look at something really basic. Something really, really basic. Or of course, always, bro, what? Yeah, always we want to substitute 0, right?
We
So
can
when we
do x
substitute
equal to minus 1
x equal to minus
to
1,
make the RHS 0.
okay, what do we get? We get, if we substitute x is minus 1, then this becomes 0, because this is minus 1 plus 1, 0. And this becomes minus y. So we get, it is always true that f of y, f of minus y, plus f of y, this is always going to be 0. Crazy. So if f of y is 0, then f of minus y is 0. Wow. So if f of y was 0, which means f of y could not be y, then f of minus y would have to be 0. Okay. So we've reduced it a little bit. Now what?
We have not even done x equal to 0, right? Like the first.
Yeah, I haven't substituted that.
By the way, here y can be any real number, right? Y has to
Yes,
be.
yes.
So now we're done, right?
How?
If f of minus y is equal to 0, then
How?
you've got f, right?
We can get like 4 times fy equal to fy, but I don't know if it helps.
What?
4 times fy equal to fy.
4 times fy is fy. How?
Like using a minus f minus y equal to f of y. We can get that.
How? I mean, what are you doing there?
I was putting y equal to fy.
And then y is equal to fy. Sure, let's put that in.
Then
Y-
y की जगह minus
y is equal to y, and then y की जगह,
minus y.
I mean, you've already put in f of y. Are you putting in f of minus y?
Yes, yes.
Okay. So we get then f of minus y plus f of minus y. This is 0. So what? This does not really give anything.
Wait. What substitution are we doing?
Wait
We
one second.
substituted into this equation, we substituted f of minus y, but that doesn't really appear to give anything. I mean, of course, like it's a really good thing that you're trying out the triple f thing, right? Because you have f of y here, so you can try to put in f of y, and you'll get what you will get. Of course, is f of minus y. This is equal to f of minus f of y, but yeah, not much apart from that.
Can I
So
just
basically,
something? I
just one
don't.
second.
Yeah, but
Just
sure.
one second. Just one second. Just one second. So what we've reduced it to, I'll just state this right now. What we've reduced it to is f of minus y is either equal to 0 or f of y is equal to y. This is what we've reduced it to, right? If we can show that there is only one value of y that is equal to 0, if we can show that only f of 0 is 0, which it is true by the way, like if we substitute 0 comma 0, then we'll get f of 0 is 0, right? Because this becomes f of 0, the first term. This becomes f of 0. This becomes f of 0. So f of 0 will be 0 because these two things cancel out. So if we can show that 0 is the only value such that f of 0 is 0, then f of y will be y for everything because f of 0 is also 0.
Can we consider p of x comma minus y?
P of x comma
original.
P of x comma minus y in which equation?
In the problem statement.
Okay, cool. P of x
So
comma.
RHS is just 0.
One second. This is kind of laggy. Okay, So what we will get if we put in minus y is f of x y. No, what?
F of minus xy plus double f of minus y. Wait, double f of minus y is also 0, right? Is equal to 0.
If f of minus y is 0, then double f of minus y is 0.
And f of minus y is 0 implies the RHS is also 0. So basically, if f of minus y is 0, then f of minus xy should be 0 for all other x.
Yes, wonderful. So if f of minus y is 0, what we have concluded now, if f of minus y is 0, then f of minus xy is 0 for all other x.
So we can achieve all values from this, right?
Exactly. If y is not equal to 0, then like suppose there is some value, what we are saying is suppose there is some value y such that f of minus y is equal to 0 and y is not equal to 0. Then what we have is f of minus xy is equal to 0 as well. But x can be anything, right? X can be anything, and varying x over the reals, we'll get that f of all reals, like any real value you take, f of all reals will be 0. So if there is some value y not equal to 0 such that f of y minus y is 0, then f of x is equal to 0 for all reals. But if there is not such a value, then we know that like if this is not true, then this must be true. So I hope it is clear now that the conclusion is either f of x is equal to x for all x, or f of x is equal to 0 for all x.
Why can we not conclude this from the fact that f of minus y is equal to 0? Here, f of minus y equal to 0 is an identity, or what is it?
Y is a certain value.
Oh yeah,
Y is a
sorry.
certain.
Yeah. So for some y, either f of minus y is 0 or f of y is equal to y. This is what we
Okay,
have.
for a particular y. Okay, yeah,
Yes,
got it. Yeah,
for a
okay,
particular
yeah,
y we have.
yeah, got it.
Why we have that is because y is okay. Sorry, we have that because yeah, f of y is not equal to 0 for a particular value of y. That meant that f of y is equal to y, and we got that. Yeah. So the contrapositive of that is like f of y is not equal to y, f of y is 0. So they're like optional. If f of y is 0, then f of y is not y, and if f of y is y, then f of y is not f of not
Yeah,
0.
yeah, I got it.
Yeah, for a particular value y. And then we got that f of minus y depends on f of y from this thing. No, from something. Somewhere we got that. So yeah, from here we got that. If f
Yes.
of y is 0, then f of minus y is 0.
It's fine. Thanks.
Cool. So that was post cancellation, and it's really powerful. You can see that we immediately just annihilated infinitely many cases. We just got these many cases left. So it's really powerful, and we are over time. So there are some things I did not cover, but it's fine. It's mostly fine. For example, from here, if we had something like f of y is equal to 0 or f of y is equal to y for a particular value of y, this does not mean that the whole function. This does not mean that f of y is 0 for all y or f of y is equal to y for all y. This does not mean that, by the way, because this is only a particular value of y. It can be true that f of 1 is 0, but f of 2 is equal to 2. And f of 3 is equal to 0, but f of 4 is equal to 4. Something like that. That can happen. And getting stuck in this trap of thinking that this is true for all values of y, thinking that it's an identity, that is called the pointwise trap. And you want to avoid that. You don't want to get stuck there. That is instant zero. Like instant zero marks, not instant zero function. But yeah, finally we can just take these values of function. They work because 0 plus 0 is 0 and xy plus y is x plus 1 times y. Pointwise, yes, pointwise trap. Cool. Yeah, so this is all. I had a lot of problems planned. We didn't really discuss a lot of problems, so they're all gonna go to your preset. Make sure to try the problems. Functional equations are really fun. I mean, they have fun in their name. Functional equations. So yeah, without practice, with practice, functional equations are going to be really easy. Without practice, functional equations are going to be, yeah, practice makes perfect, right? So yeah, thank you. That's it for today. Any questions you have, asked me on Discord. My Discord is in the loop. I've sent it in the chat. Any
I just
questions you
want
have?
to ask you, somehow we get like some number of f of y equal to f of y. Then how does it help in a problem?
What? Wait, can you repeat that?
Like some number of f's, like 4 times f, let's say, and y equal to fy. No, 4 times f matlab 4 बार ही है.
F of
Oh, was that what you were trying to say over here? Like over here?
Yeah.
Oh, I thought you were saying 4 times f. Oh, okay. So you're saying f like 4 times or whatever of y. This is equal to
fy.
f of y. Okay.
Like I just want to ask, can it help in a problem like somehow?
I mean, in some cases it can help definitely. I mean, with 4 f's over here, it might not really be very helpful. But suppose you have like injectivity and you have, like, I discussed this already, but if you have injectivity and you only have this much, then you can just cancel out the f's and you will get f of y is y, which is really cool. I mean, that just solves the problem. Over here, if you have injectivity, then that would give f 3 times y equal to y. This gives surjectivity, so that's also cool. So, but you need to have injectivity for surjectivity to hold. So yeah, it can give some things.
Okay, thank you.
Yeah, fine. Okay, cool. And what else? Yeah, I mean, these types of things you will see in probably a class that will be held later. Like these kind of iterative things, like you are like 100 times f y is equal to some y plus 25,000, like 25 of y or something like that. You'll see in a class called arrows. But yeah, I'll stop recording for now. Stop recording.